Today we have both student presentations as well as keynote addresses. First of all, we just want to say thank you to our 2021 CALMS conference sponsors. All of these entities have donated money to CALMS that allow us to support our student scholarships. And one way you can help us support them is to play our sponsor bingo. We have 8 $25 Amazon gift cards available, and so far we only have 10 entries. So right now your odds are pretty good. And we will drop the link to the sponsor bingo in the chat so you can play. It just takes a couple minutes. We also had our business meeting on Tuesday, and I would just like to congratulate all of our newly elected CALMS officers. Mark Silos will be taking over as president, and then Byron Furman will be our president-elect for next year. If you were thinking about attending NALMS 2021 but didn't want to travel, it is now virtual. So if you follow the link up here, you can get more information about attending NALMS 2021. I think the registration's around $200, so it's significantly cheaper than going all the way to Oklahoma City to present. So I would encourage you, if you've kind of thought about going but are a little bit hesitant, to check it out again and consider attending this year. And then just kind of some housekeeping announcements. I'm going to close the sponsor bingo on Tuesday. We still have the gift cards, so go ahead and enter that. If you don't mind muting yourself and turning off your video, feel free to grab your lunch. We are recording these presentations. We will have a chat, and you can place your questions in the chat. It's very important, because we have 4 students today, that you place the name of the student to whom you are questioning in the chat. Otherwise, it might just get really confusing. And then Mark Butel is going to take over and introduce our student scholarship winners, and then do a Q&A, and then we'll close out the day with our keynote address from Craig Williamson. And before I hand it over to Mark, I just wanted to share my favorite XKCD comic in honor of Student Scholarship Day. And I know some of our students are probably pretty close to defending, so I would just like to remind you that the best thesis defense is a good thesis offense. So Mark, take it away.
Great. Okay, well, good afternoon, everybody. I'm Mark Butel. I'm a professor at UC Merced, and it's my pleasure to host the scholarship component in the presentation. So I just wanted to remind people that the 2022 Lake Management Scholarship announcement will be coming out shortly. It will be the same format as this year for scholarships of $1,250. And it's eligible to full-time students, both graduate and undergraduate, in an accredited California, Arizona, or Nevada college or university. Hawaii is included here as well. So please get the word out, and don't forget, it's a pretty reasonable application procedure. It's a resume, unofficial transcripts, and a summary, 500 words only. So it's got to be targeted and well written of your summer plans for 2022, and a couple letters of rec. So with that, I'm going to give brief introductions on our 4 winners. And you may have seen in the just really wonderful CALMS newsletter that was developed, it had bios on the students. So I'm just going to go through the 4 students. This is also the order they'll present in. So Jeffrey Belding is a PhD student in mathematical sciences at the University of Nevada, Las Vegas, and he's going to talk about modeling filtration of Lake Mead water. And then we have Kenneth Larrieu. I'm not sure I'm getting that. He'll correct me on that when he presents. He's a PhD student at UC Davis in civil and environmental engineering. And he's going to talk about the effects of wildfire on suspended particulate matter in freshwater lakes. And then we have Shelby Defeo, a PhD student in environmental systems at Uc Merced. And Shelby, her scholarship was supported by Aquatechnics. So thank you so much to Aquatechnics for that support. They have 40 years of water resource protection experience. So check them out at www.aquatechnics.com. Shelby will be presenting on the effects of oxygen on nutrient metals release from eutrophic lake sediments. And then finally, we'll wrap it out with Sergio Valbuena. Sergio is a PhD candidate at UC Davis, and he'll be talking about littoral zone limnology and rotationally influenced lakes, so big lakes. And his scholarship was supported by Clean Lakes, Inc., Aquatic Ecosystem Restoration and Maintenance. And check them out at www.cleanlakes.com. It sounds like we want to hold off the questions till the end. Is that right, Dina? Or should we do questions at the end of each presentation?
Mark, if you would prefer, you can just do questions at the end of each student presentation if that makes it flow a little better, for sure.
That sounds good.
Okay,
and these
great.
are going to be short presentations, 10 minutes or so, a few questions, but please step up and ask questions. They can be general in nature, they can be focused in nature, but yeah, please stay engaged. So I will stop sharing and we'll start off with Jeffrey Belding.
All right, can everybody hear me?
Yes.
Bring up my face now so everybody can see me here. I'm gonna share my screen. Okay, can everybody see the slides here?
Can.
Slides look good.
All right, perfect. All right, so let's get started. So yeah, it's actually good that we're gonna do Q&A after the presentations because I actually have to teach at 1, so I was gonna have to cut out a little early here, but now we'll be able to get me to answer some questions here in case you guys have any. So I'm going to be giving a presentation on modeling filtration at Lake Mead, and specifically I'm going to be going over what's called the run-to-run control model for membrane filtration. So let's go ahead and dive right in here. Gotta click there. So we have lake management and water treatment models. Basically, the goal of this research is to help inform the River Mountains facility of maybe better ways that they could operate their water treatment plants. In particular, I'm looking at the filtration processes. So right now we have some Lake Mead modeling, which is done by the AEM 3D model. I believe it's aquatic ecosystem, and I can't remember what the M stands for, but it's a 3D lake model that basically gives us a lot of data, and then it's fed into a surrogate lake model, which further processes and gives input into the water treatment process model. The water treatment process model is the part that I'm working on. So basically, we have a bunch of data coming in from the Lake Mead, all sorts of stuff, given like you know, the turbidity of the lake, raw water quality, all sorts of different qualities of the water that were coming in. We have data that comes in about this. It feeds to the surrogate lake model, which then feeds into the water treatment process model, which I'm working on. Again, membrane filtration is a very key component to the water treatment model. So you have kind of an overview of the whole plant here, right? This kind of building where we all work in, and then you see different components of the plant, but the main component here is this giant grid of 20 filter beds. And these are the beds that I'm actually going to be modeling, this stuff that I'm going to be talking about today. But again, like the goal is to basically inform ourselves of, you know, how we're operating these plants right now, because most water treatment plants and filtration systems are operated more or less based on experience, like, you know, what works best, you know, how long should we run these filtration and backwashing cycles, what kind of flows we should be putting into these cycles. All of that stuff is kind of determined, you know, by, you know, trial and error over time, what works best. And so now we're kind of investigating, well, let's see if we can model this sort of stuff mathematically and see if we can come up with a better way to determine these sort of set points for this operation. And the advantage of this modeling is it's not just restricted to just normal water quality scenarios. We can model all sorts of different raw water quality scenarios. So we can model, water coming in right now, or maybe, water coming in the future when the lake levels are much lower and, sediment concentrations are much higher in the water present. So we can kind of inform ourselves of, future planning for these types of scenarios. So again, what is the membrane filtration run-to-run model? I guess this slide kind of says what I've already said before. It's basically an output from the main surrogate model. We have all the feeds coming in from different parts of the process, goes into the filtration, and then we take all that data incoming and we run it through this model. And our goal is to basically minimize the membrane fouling, which is basically over time, right? We have a membrane that is actually doing the filtering. In the case of river mountains, it's 2 layers of anthracite, coal, and sand. It's just a gravity-based membrane. So the water is pushed through by its own pressure. And our goal is to minimize the amount of fouling, so the amount of gunk that gets really stuck inside of these membranes, and also minimize the overall cost of operation by controlling 2 basic things about the process, which are the time periods for which we do the actual filtering, and the membrane backwashing, which backwashing is when you kind of reverse the pressure and basically push all the gunk that is accumulated during one filtration cycle out, and then you wash it all away. So it's basically a filter cleaning process. So we're going to control the time period, or we're going to try and figure out the best way to control the time periods for those membrane filtration and backwashing cycles. And then also good set points for the fluid flux, or how much water we're pushing through into these cycles. And so scheduling strategies typically go like this. Whenever you're running a filtration process, you always have like a long period of filtration. So at the river mountains, these filtration periods typically are around 175 to 200 hours of runtime. And then we also have kind of a downtime where we do many different things. We can run filter to waste operations, also backwashing operations, and just general maintenance that may or may not be needed during the downtime when we're not running filtration. And what this model seeks to do is to model what is known as the membrane resistance, or how well the membrane filters out certain water, how well it resists water going through it. And so this membrane resistance, you can imagine that as you filter more and more water, at the start, the membrane's kind of clean. So not a lot of water flows through, but then over time, the resistance gets longer because more and more water builds up, or more and more fouling builds up on the membrane itself, more gunk, cake layers and stuff like that. And then eventually it'll get to a point where it's too bad. Usually we're either getting like too much pressure from the water, or too much cake buildup on the membrane, many different reasons why we'd say, okay, let's stop filtering and let's start a backwash cycle. So then in backwash, right, all of that cake layering gets, and gunk in the membrane gets washed out, right? You pump water back through the membrane, and then this forces all the gunk out, and it reduces resistance down to a nice level where we can then start running filtration again, and then pump it back out, just keep doing this over and over and over. And that's just the life cycle of the filtration cycle right there. And so what this model does is you normally have controllers that kind of control how the fluid flux and like the timing of these processes. But then in the backwashing, there's some time, some downtime where we can, do maintenance and stuff. So during this time, the run-to-run controller will kind of analyze the physics of the situation and try to modify the model so that different irreversible effects that may come up in the membrane due to like just irreversible fouling, for instance, like certain gunk gets stuck and then it can't get removed. So that wear and tears on the membrane over time. And so this model will adjust certain parameters to account for the fact that over time, this membrane is getting older and it's getting strained and it's getting used. And so that's going to be the usefulness of this scheduling strategies. In between, we'll kind of adjust the model so that it runs the set point slightly differently for the next filtration cycle. And then this is basically the idea behind the run-to-run controller, right? You have up here, you have basically the normal type of processes that you would see, and the normal kind of controller process that you'd see. You'd have a base control, which sends you some set points into the process, and then the process realizes those set points. So in this case, it's usually fluid flux and time to run the process. And so then the PID controllers inside our plant will make sure that the fluid flux stays at these particular set points throughout the operation. And then once the process is done, we feed data back into the base controller, and then the base controller, or actually this is happening continuously, where the process is always feeding data back into the base control, and the base control is continuously making sure all these set points are met. But what will happen in addition is we're also going to send this data into the run-to-run controller. So in between cycles, when this thing isn't running, the run-to-run controller is going to do what's called a parameter update, where we update the model to represent the new physics, right? The new wear and tear on the membrane. And then using this parameter update, we'll come up with new set points for base control. And usually to advise these set points, we have an input known as the cost, right? In this case, we'll look at the cost of running the plant and cost of running the different parts, the air scour blowers, and also the cost of replacing the TMP, which is the transmembrane pressure, or cost of supplying power to the TMP, I should say. And so once the run-to-run controller does its thing, it will figure out these different set points, and then it informs the base control, okay, this is how we should run the model for future cycles. And so I talked a little bit about, or kind of hinted at it earlier, transmembrane pressure, which is basically the variable that we use to make this model work. So this model is based on Darcy's law, which is the flow of water through a porous medium, which is exactly what we're talking about. We have a membrane that has water flowing through. This basically, Darcy's law has this formulation where it's the pressure of the water is equal to the fluid flux times the viscosity of water times the resistance of the membrane that it flows through. This is kind of like the state equation that controls how these variables relate to each other. So in the plant, we have the fluid flux, like we can measure that from our plant measurement data, the stuff that we have for inputs. We also have access to the fluid viscosity, and we have access to transmembrane pressure measurements. So this model really takes those three inputs and then tries to calculate a membrane resistance, which we can then use to formulate a cost equation and run basically an optimization problem that minimizes the cost based on the inputs of how long do we run the filtration, how long do we run the backwashing, and then what do we set the fluid fluxes at for each of those cycles. So that's what the transmembrane pressure is used for. And then this is about the most math I'm going to throw at you guys. As typically we like to black box this stuff, but I guess it's kind of good just to see some of the stuff that goes in. So this is the base equation for the filtration phase resistance model. And I am kind of simplifying it a little bit for you guys, but essentially the filtration phase, it depends on two different things. The fluid flux that's going in, and essentially what this equation says is the more fluid flux you put in, the more the resistance is going to change over time. So higher fluid flux means the resistance going to increase more and more over time. In addition, this model also accounts for cross flow that is present during filtration. And funny enough, River Mountains actually doesn't do any aeration cross flow during filtration cycles. So for my modeling, I actually end up setting this term equal to 1 and it just kind of disappears. But in general, if you have cross flow aeration in your filtration phase, then this part will capture that behavior. And one of the reasons this is run-to-run control is in order for me to run this equation, I need to have values for this M, this alpha, this beta, and then this coefficient here. We actually determine these using a least squares method. We basically compare the TMP that we see from any given filtration cycle, and we compare that to what we think the actual resistance model should be, and then that will help us determine these numbers. The problem is there are 4 different numbers to determine, and on any given one cycle, we can't determine all of these numbers simultaneously. And this is the advantage of the run-to-run control. What we can do is we can kind of do a little bit of a compromise. We'll say, okay, every cycle, we're going to just determine these 2 parameters, M and R naught F. And then after that, over longer cycle periods, so over, for example, in our case, we do 3 filtration backwash cycles in a row. We'll actually estimate alpha and beta over longer time horizons. And so this dual control problem is something that's present in a lot of systems where you have a lot of parameters going into modeling something. And so one way around that is to update some of the parameters on every cycle and then update the rest of the parameters over longer cycle periods. And so kind of over time, this dual problem just updates itself, and it just makes it a lot easier instead of having to find set points that are we're not really sure of, because if you try to update all 4 at once, there could be an infinite number of solutions to do that. So hopefully that wasn't, too much math for you guys, but this is the kind of stuff that kind of goes in and we black box it and pump out the actual results for it. But I thought it would be interesting to show everybody. And then, so the filtration model is pretty bad. It turns out the backwashing model that was proposed is even worse than that one. And in fact, it's so bad, I don't want to say it's bad. It's just, it's so complicated that it's very difficult to realize in real time. In fact, if you look at the paper which this model is from, you'll see that they even say they couldn't realize this model properly. And so what we did to kind of get around that is we come up with an approximation for all of the backwash parameters. And essentially what we do is we set it equal to, we set the fluid flux and the resistance equal to the fluid flux that we observed from the previous filtration cycle. And in fact, later on, what we'll do is we'll model the fluid flow for the backwash in terms of the actual measured data from the backwash of the previous cycle. So we have the fluid flows during the backwashing, and then we just set the fluid flow for backwash equal to what we observed. And it is an approximation, so it isn't entirely accurate, but we can kind of justify this approximation just based on the fact that backwashing cycles are so much shorter compared to filtration. Usually backwashing takes anywhere from 30 minutes to an hour, whereas filtration takes like 200 hours. So because it's so much shorter, we can get away with this approximation and not lose too much accuracy in the process. But getting around this sort of approximation is still a very active area of research, and a lot is going into what we can do to more properly model backwashing phases. Because the real problem is just during backwashing, the flow is so much more turbulent and it's so much harder to capture the dynamics within, especially with
Jeff, we got to move on to the next ones. Do you have a wrap-up slide or?
Yeah. So basically, next part is just to minimize the cost, which I kind of already talked about. And long story short for this, the model is okay, but it predicts very small filtration times. And so we're going to be doing more work to try and model this a little better. I'm exploring Markov chain Monte Carlo methods, the DRAM algorithm, and we're also exploring a new machine learning algorithm for trying to understand these processes more. So sorry for going over time. If you have any questions about this, you can contact me here, or I don't know if there are any questions for me now.
Great. Thanks, Jeff. I think what we'll do is we'll move on to the next speaker, and we will have kind of a community questions at the end, time permitting.
Okay, I apologize.
You won't be here. Anyone have a quick question for Jeff? He's got to go teach. I assume it's a math class?
Yeah, it is.
Sure it is. All right. Real quickly, Jeff,
yeah.
membrane. You're calling it a membrane. Is it like a thin membrane, or is it sounds like it's layers
No,
of
it's actually not a membrane.
particles.
I did say it earlier. It's about a 2 meter thick. It's 2 layers. One layer of anthracite coal. I believe it's about a meter and some change thick of anthracite coal, and then below that there's a sand layer as well.
Yeah, so it is
That's what we're basically modeling as the membrane.
Yeah, cool. It's a classic sand filter bank for water filtration.
Yes.
Yeah, in a way, it's a big membrane.
Yeah, it's just.
Thanks so much. Good luck with your work. It really looks fascinating.
All right, thank you very much. Thank you for having me.
DRDT in there as a professor. Okay, thanks, Jeff. Let's move on to Kenneth Larrieu. And Kenneth, come on in.
Okay.
And let's hear about some wildfires. Big topic in California.
All right. Can everyone see my slides?
Yes.
Cool.
And we
All
can
right.
hear you. Thanks.
Great. So hello, everyone. My name is Kenny Larrieu. I'm a PhD student at UC Davis. And today I'm going to talk about some research we've been working on looking at the effects of wildfire smoke on particulate matter concentrations in Lake Tahoe. So first of all, in the last few years, California has seen a lot of record-breaking wildfires. So there's this graph that Mark shared earlier showing the 20 largest California wildfires, and most of them have been just in the last few years. And so with the increasing magnitude and frequency of these large wildfires throughout the West, especially in California, it's especially important that we understand the impacts that these are having on our freshwater bodies. Specifically, we were looking at Lake Tahoe, which is ultra-oligotrophic with a 600-year residence time. It's known for its clarity, but it's lost some of that since the 1960s. And because of that, there's a lot of effort that's been put towards limiting the nutrient and particulate inputs into the lake. So then fast forward to 2021, this year we had the Caldor fire nearby. It was huge. It burned an area almost twice that of Lake Tahoe itself, and it caused weeks of hazardous air quality in a Lake Tahoe basin. The impacts, the atmospheric deposition of wildfire smoke on the lake clarity and particulate matter is unknown. And so that's something that we set out to determine. So how we did that was using a glider. Glider is a buoyancy-driven autonomous underwater vehicle. It's this big yellow thing. And essentially it has a bladder that it's able to expand and retract to adjust its buoyancy. So it creates this vertical buoyancy force that it's able to change. And then the wings that it has then converts that into forward thrust. So in this way, it's able to zigzag up and down, traveling through the water. So the sensor that we have equipped on it is called a laser in-situ scattering and transmissometry sensor, or a LIST for short. It's this black thing on the top here. And essentially how it works is it shoots a laser through this control volume, and it uses the light diffraction patterns that are produced on the other side in order to infer particle size distributions in the 1 to 500 micron particle size range. And so this is really cool because as opposed to one single bulk value like turbidity to quantify the clarity of the water and the amount of particulate matter in there, we're actually able to have a breakdown of particulate concentrations in all of these different size classes spanning 1 to 500 microns. So essentially what we have for our measurement platform is a glider with freaking laser beams attached to its head, which is a little bit more reliable than our previous measurement platform. So for this study, we continuously sampled for over 3 weeks from September 3rd to 25th. And we alternated going back and forth along these east-west and north-south transects spanning the lake, going up to 150 meters in depth. And it took about 20 minutes for each dive or climb, which gave us a vertical profile. So first off, looking at the air quality data for this period, here we have air quality from a couple hundred sensors around the basin, giving PM1 PM2.5 and PM10, which is the particulate mass concentration in the air for particles smaller than 1 micron, smaller than 2.5, and smaller than 10. And the two main trends I want to point out here is that from the 3rd, when we deployed the glider, up to about the 11th, during that period, there was a dramatic improvement in the air quality and decrease in these particulate concentrations, and that it was primarily composed of small particles that are less than 2.5 microns. So remember, the list measures 1 to 500 microns. So these are very small particles that we're getting from the wildfire smoke that are ending up in the air. So now looking at some of our glider data, we have depth on the y-axis. This first plot here is showing us temperature. And we see that about 25 meters depth, we have a very sharp thermocline spanning about 15 degrees Celsius temperature difference. And so what that strong thermocline does is the changes in temperature, they change the index of refraction of water. So for the list, what that means is that it's bending the laser light. And so it's causing us to get erroneous readings in this region where we have a really sharp thermocline. And so because of that, in the following plots, I've grayed out that band there. I filtered it based on buoyancy frequency to filter out these areas that are getting erroneous readings due to the optical properties of that thermocline. The second plot here shows the overall particulate matter concentration. And we can see that actually throughout the entire glider deployment, it didn't appear to really change much at all. And as I'll show in a second, the reason for that is that the overall particulate mass concentration is dominated by these size classes that are larger than 10 microns and larger than these smaller sizes we're seeing in the wildfire smoke. But then looking at this side, at the size class that corresponds to about 2.5 microns, so again, representative of these wildfire smoke particles we're seeing, we do see this clear trend over time of the concentrations decreasing as it's being removed from the water column. And we're seeing that it's clearing out a little bit more in the hypolimnion, and there's more of this very fine particulate matter that's hanging around in the epilimnion. This last plot here is showing our beam attenuation coefficient. And so essentially that's a measure of how much light is attenuated as it travels through the water. So in essence, the measure of the cloudiness or turbidity of the water. And we see the same general trend as we saw for the 2.5 micron concentration, in that the water clears up over time with it getting clearer in the hypolimnion and still staying a little bit cloudier in the epilimnion. So now comparing that side by side directly with the air quality data again here, these lines are just showing the average value of the beam attenuation coefficient for the epilimnion, or the average for the upper 30 meters, and for the entire 150 meters that we covered with the glider. And so we see that for, in both cases, this light attenuation is gradually decreasing at the same time that the air is clearing, indicating that there's this corresponding improvement in the water clarity. And about 2 weeks after the air cleared up, both the epilimnion and the hypolimnion recover these attenuation coefficient values that are typical for this time of year in Lake Tahoe, and what has been seen in years past without as intense wildfire smoke. Breaking it down, specifically looking now at the particle distributions, we have on the x-axis the diameters. These are the different size classes, and then on the y-axis we have concentration. And there's one line plotted here showing the median value for each day going from the 3rd to the 25th. And so we can see here that this highest concentration here, remember this is a log scale, so this is by far the highest concentration, is for this larger size class, and it's larger than the particulate matter that's present in the air in the wildfire smoke. So this actually did not change very much throughout the entire glider deployment. But we see for particles smaller than about 10 microns, there's this very clear pattern where over time, the concentrations are decreasing for these smaller size classes by orders of magnitude. And the interesting thing about this is that despite the fact that these small size classes that correspond to the wildfire particulate matter, despite the fact that they have lower concentrations than these larger size classes, they have the greatest impact on water clarity. That's why we didn't really see any correlation between the overall particulate concentration, which is relatively constant, and the beam attenuation coefficient, whereas the beam attenuation coefficient had the same pattern that we saw as like the 2.5 micron size class. Interestingly, we also see that this largest size class has the same sort of pattern as these small ones. And we're still not 100% sure why that's the case, but one theory is that we actually have particles that are smaller than the 1 micron resolution limit of the list. And from this paper, it's a known issue that when you have particles that are smaller than that resolution limit, it will cause erroneous inflation in the largest size class concentrations. So that might be why we're seeing some of the same signal and same pattern for these largest size classes. So then we can compare this to the theoretical settling velocity of a particle as a function of its diameter and its density. This is called Stokes Law, and it's basically a balance between gravity, buoyancy, and viscous drag. And so from that, we're able to determine the time that it would take for it to settle a distance of 150 meters, so essentially to be out of sight from the glider. And we see that in 1 month, even if we have very dense particulate matter, we would only settle out stuff that's larger than about 8 microns. So this doesn't explain why we're seeing these much smaller size classes that are being removed much faster from the water column than the settling velocity would theoretically suggest. What that tells us is that there is possibly some other process that's removing them from the water faster. One could be flocculation. They could be joining together to form larger particles and settling out faster, maybe consumed by zooplankton. They could be building up in that thermocline region that we can't resolve because of its optical properties, or there could be some other process entirely. So then for our future plans, what we want to do is try and continue to monitor the seasonal variability in particulate concentrations, combine our list observations with both microscopy and chemical analyses to determine what this particulate matter is composed of and what implications there might be for lake productivity. And then combining hydrologic and air quality data to then identify exactly where all of this is coming from and what our sources are for our particulate matter. So thanks, that's all I have for today. Thanks again, CALMS, for the funding, and as well as others. And thanks to the entire Turk field team for all the logistical support that made this possible.
Great, thanks, Kenneth. You have time for a question? Just do not feel, just go ahead and unmute and ask a question if you have one for Kenneth.
I have a question.
Yeah.
Firstly, that was a super cool presentation. Thanks a lot for that. I was wondering, so you showed the particle distribution map, and it looked like the one that wasn't really changing over time that you assumed to be kind of background was like 10, actually it was about what?
Like 11 or 12
11 microns or something. Could that be like just phytoplankton, or do you think phytoplankton is represented in that particle size distribution at all?
It could be potentially, to be honest. I don't know a ton about phytoplankton, but I think that that would be the power of, like I said, combining this with microscopy and doing chemical analyses on like water samples to then actually see under a microscope and see like what it's composed of, right? You can see the plankton, or you can measure like if we have nitrogen or what the constituents are, and then sort of parse out like what are these specific signals that we're seeing in different size classes.
Awesome, thank you.
Yeah, interesting connection there, Kenneth, is I think the productivity can go up during these wildfires because of these particulates of nutrients, and photo inhibition is relieved a bit. So yeah, you're out there during a dynamic time.
Yeah, so like we're seeing this clarity improve like due to the optical properties of the particulate matter, but there could be some secondary effects where it then increases productivity and that could be delayed. There's a paper that came out just a couple of weeks ago in Nature that was looking at the Australian bushfires in 2019 and 2020. And they found that that fertilized the Southern Ocean and caused this gigantic phytoplankton bloom. And so, yeah, it's pretty incredible.
Great. Well, thank you. And all the lake managers and folks out there could only wish for the clarity.
Yeah.
Although it's decreased quite a bit.
Mark, can I ask a quick question?
Sure.
It's almost a yes or no. Were you able to collect any samples from the metalimnion to see if you actually did have particle accumulation?
So that is, yeah, that's something that we've been looking at and we're looking at now, but we still need to get these water samples analyzed. So hopefully we'll have an answer to that soon.
Yeah, really interesting to have this high tech, great monitoring, and yet have a zone within the water column that is kind of really unavailable to you. Must be frustrating.
Oh yeah.
Okay. Yeah, thank you.
Thank you.
All right, great. So next up, we have Shelby Defeo from UC Merced.
Hi, let me get my screen ready to share with you all. I hope that that's visible for everyone and that everyone can see and hear me.
It is, and we can hear you. Thank you. Go ahead.
Okay, perfect. Hi, as Mark said, my name is Shelby Defeo. I'm a second-year graduate student at the University of California, Merced. And the project I've been working on since about May of this year is the effects of oxygen on nutrient and metals released from eutrophic lake sediments. And so to give you a little bit of background, the lakes we've been working with are Lake Henshaw and Lake Wolford. They're located in Southern California in kind of that like greater San Diego region. And they're managed by the City of Escondido and Vista Irrigation District. And they're a really important part in water security for the City of Escondido. The City of Escondido serves about a population of 150,000 people. And these two reservoirs are an important part, providing 20 to 30% of the city's water supply. If you take a look at the figure on the right as well, you'll see that there's two different colors of water. So we have this dark blue that represents local water and a light blue that represents imported water. So Lake Henshaw and Lake Wolford are local water, which in California, having local water is really important because imported water can be expensive or allocations can be iffy during drought years. So having safe and reliable water supplies that are local are a really important part of resiliency and like building water security into our climate change plans. However, the quality of these reservoirs has been degraded in recent years. There's been issues with harmful algal blooms. And when we think of algal blooms, a lot of times we think of external nutrient loading. So that's your runoff from fertilizers, your leaking of septic systems, but you can also have internal nutrient loading. And that's what we're seeing in these reservoirs is that you have this release of metals and nutrients from the sediments already inside the reservoir. So my project is hoping to examine that. For this project, we really have two study aims. Our first is to quantify anoxic sediment release rates of nutrients and metals to the overlaying water. And the second is to assess the effects of dissolved oxygen on sediment, nutrient, and metals release rates to inform potential lake management strategies like destratification, aeration, or oxygenation. So ultimately, we're hoping to collect data that can inform what the management of these lakes should be so that we can preserve that quality and assure that water security for years to come. So we sampled Lake Henshaw in June of this year and Lake Wolford in July. If you take a look at the maps on the right, those are our approximate sampling locations. We sampled at 3 locations in each lake, as well as taking a sediment-only sample from Lake Henshaw just to add an extra data point. And to sample, what we used is an Ekman dredge. So we dropped it down to the bottom of the lake, got a little bit of sediment and some of that bottom water, really tried to preserve that bottom water and sediment interface, pulled it back up to the surface. And if you take a look at the picture on the left, there's that clear chamber. So that actually comes apart. And we were able to take the cylinder, stuff it into the dredge, cap it from the bottom, pull it back out and reassemble our little contraption. With the goal of trying to disturb the sediment water interface as little as possible and really try to get a representative sample. We then collected bottom water with a Van Doorn bottle and very slowly drifted into these chambers to fill them to the top, again, trying not to disturb that sediment water. And once they were full, they were pretty stable and we could transport them back to our lab in coolers on ice. And so once back in our lab, we set them up as you see there on the right. We had 12 chambers per lake. So we had 3 sites, which was designated by 3 different colors of tape on our chambers, and 4 replicates per site. So that's how we end up with 12 chambers per lake and 24 chambers total for the 2. Each chamber was taken through 3 different oxygen stages. They each began under oxic conditions. So that's just us bubbling these chambers with air. And so we took the oxic conditions for 9 days. And at the end of the 9 days, we refilled our chambers with lake water with the idea to like simulate algal addition and the mixing of water that happens naturally within the reservoir. We then did a 9 days of hypoxic air, which had a lower oxygen concentration than just what we breathe. And we also refilled at the end of those 9 days and then did a 12-day anoxic period. We decided to take the anoxic period a little bit longer just because we believed that that's probably where we would see the most interesting action. And so we wanted to make sure we really captured the whole story there and took it as far as we needed to. So we did collect water every 3 days from these chambers. We took about 50 milliliters out with a syringe and then placed that in the appropriate bottles to store for further analysis. We measured periodically the chambers using probes for pH, redox, and dissolved oxygen, as well as temperature, just to kind of get a general sense of what was going on within our chambers and to make sure that things were happening as they should, nothing funky was going on. For temperature, we tried to keep the chambers at about 25 degrees Celsius. These are relatively shallow and it's in the summer, so they would be pretty warm naturally. Unfortunately for our lab, that meant keeping the entire lab at 25 degrees Celsius all summer, so it was a pretty warm one for us. So then with that water we collected from these chambers, we were analyzing for total iron, total manganese, SRP, the soluble reactive phosphorus or phosphate, sulfide, ammonia, and nitrate. So this graph is from our Wolford Dam A site, so one of those 4 chambers at the dam for Wolford. The idea in showing this was just to kind of give an idea of what we saw throughout the progression. So what we saw is that the chambers are pretty alkaline. The pH remained around 8 for the duration of the incubation. And that we saw what we wanted to in terms of oxygen. We have the DO around 8 milligrams per liter. During our oxic phase, so very well oxygenated, it drops down to about 1 milligram per liter for our hypoxic, and then we're at our 0, no oxygen for the anoxic phases. Redox, we also see trends that follow what we would expect. It's pretty steady during the oxic and hypoxic, which as long as there's some oxygen around, redox tends to stay pretty stable and in that positive realm. But once we moved into our anoxic phase, we saw it really decrease to that about negative 100 millivolts. So I thought that this was kind of just an interesting thing to see how they all correlated and what kind of happened throughout the course of our experiments. So this is the figure on the right from our Wolford Dam set. And so this is not an amalgamation of data or anything, but it's just this one figure. But I thought it kind of showed a nice example of the trends we saw over the course of these incubations. So what we saw is that SRP and ammonia were relatively stable during the oxic and hypoxic phases, but they increased during anoxic. So kind of that last third of the graph, we really see the yellow line and the gray line shoot up. Nitrate also remains pretty steady during the oxic and hypoxic, and then becomes reduced during the anoxic due to denitrification. Manganese, so that's the orange blocks, remains steady during the oxic and hypoxic, and then also increases during our anoxic. We believe probably due to microbial reductive dissolution of manganese oxides in the sediment. Iron in here, we also see that it is relatively constant and it's staying below kind of that EPA threshold of 0.3 milligrams per liter during our incubations. We also decided not to sample for sulfide from the Wolford chambers because we weren't able to smell it. And the human nose is a pretty good sulfide detector. And so since we weren't able to detect it with our noses, we thought that that would be a pretty good reason to assume that there was low enough concentrations to not be of concern. For Henshaw, again, I selected the dam site and you chose a graph that I thought was representative of some of the things we had seen. So something of note, Henshaw did just have higher concentrations and fluxes overall compared to Wolford. And while we were actually sampling, Henshaw had significant algae on the lake, while Wolford, we didn't observe any. We see manganese increase From oxic to anoxic, so tracking that orange line across, we see a consistent increase, potentially due to the microbial reductive dissolution of manganese oxides in that like upper sediment and water interface. SRP also increases from oxic to anoxic, so could be decay of organic matter and also the reduction of iron oxides that's liberating the phosphate. Ammonia increasing, decay of organic matter there. And we also see nitrate increasing in kind of this interesting little bubble in our hypoxic phase. Then it decreases again during the anoxic, decreasing due to denitrification. Iron, we also do kind of see a little bit of a rise over the course of our incubations to levels that would be requiring treatment. And sulfide within Henshaw, it was detectable through our noses in the anoxic phase. And so we did sample for it and saw that there was some accumulation of sulfide through the time of the experiments. So our future plans, we still have some sediment data to analyze. I'm hoping to analyze for total iron, total manganese, and total phosphorus in order to just get like a full picture of the lakes and to really understand what's going on. We'd also like to make some recommendations for the planning of these lakes. Ultimately, this isn't just collecting data to collect data, but to inform management and to kind of go through the different options that are available and ultimately develop this into a dissertation chapter for myself. So I just want to say thank you to everyone who's helped me along the way with this project. We've all put in a lot of hours, and thank you to CALMS for the scholarship and the opportunity to conduct this research. Thank you.
Great, thank you, Shelby. Let's get a question from the audience. A lot of you have worked with internal nutrient loading in the management of your sites. It's a common challenge. And again, don't be shy. Just unmute and ask a question.
What can you explain a bit more about what happened with the nitrate?
Yeah, with the nitrate. So what we're seeing here, I mean, under the Wolford, we're seeing it remain pretty stable and then decrease. So we're thinking that under anoxic conditions, that's really promoting the denitrification. And so then we're no longer seeing it in the form that we were before. So the anoxic conditions are really like promoting the proper like denitrification of what we had seen in the system and just the transformation of it from nitrate.
Is there enough there to calculate that you could get that effect? I mean, that's a lot of nitrate in a way, but it's not like, I mean, you know, Mark's professor, so he's done these nitrate calculations. I just wonder if that's enough to hold off anoxia for very long.
I mean, that would be interesting. There's definitely calculations you can do, and I think that would probably be a good step to take in order to really try and get the picture of like, do we have enough here to really be like considering that as part of our management planning.
Great. Well, thank you. That was Dr. Horn asking a question there. Yeah, there's this kind of cool synergy when we have oxygenated conditions in some of these systems. We also get nitrate, which is a great oxidant too, right? So we almost get to double treat those sediments with oxygen and nitrate. Great, Shelby, thanks so much.
Is there room or time for one more quick question?
Heck yeah, sure.
Thanks, this is my great presentation, Shelby. I just had a question about what you noticed visually in the sediments in terms of coloration when you switched from oxic to suboxic to anoxic. Did you see any differences between Henshaw and Wolford? Were they black all the way through, or were you seeing like different layers of maybe oxic sediments in one lake or the other?
Yeah, so there were some really interesting, we saw a lot of worm tunnels in the sediments in like Henshaw. Henshaw definitely had the darker, blacker sediments. And we had these like interesting like oxidized layers on the top of them. And so what we did see some differences. Henshaw definitely had more of that smell and kind of that like tarry black coloration to them compared to Wolford. Had more, how I would describe it, like dirt sediments, you know, instead of like all that organic matter.
Great, thanks.
Yeah, I mean, remember the darkish kind of particulates at the end of Henshaw incubation, Shelby? What was that?
We were seeing iron and sulfide. And yeah, just really interesting.
Precipitating out, yeah. Once we had the iron and the sulfide together, yeah, they were forming precipitate. Great, thanks so much.
Yeah, thank you.
Last up, we have Sergio Valbuena. And Sergio's going to talk again about littoral zone limnology and rotationally influenced lakes. Sounds like an intriguing topic.
Let me, okay, I think I'm showing the presentation, right?
Yeah, we can see and hear you. Go for it.
Perfect. Firstly, I want to thank CALMS for the opportunity to present this research. I've been working on this since May. And this is part of my dissertation, which I titled Upwelling, the threshold for the applicability of rotational and non-rotational conceptual modes. Sorry. All right, so for a little bit of motivation and background of why I pursued this research, so far we know that in small lakes, upwelling, we expect upwelling to be at the upwind boundary, and in large lakes, in the ocean, we expect upwelling to be to the left of the wind direction, correct? And these are the two main two main frameworks that we can follow when addressing upwellings. So on one hand, we have the non-rotational or the 2D closed basin conceptual model, where we have when the wind blows on the surface, we know that the water moves along the wind parallel to the wind direction, and then we see the uprise of the deeper water column on the upwind boundary. And therefore, the motion is constrained to a vertical plane, and the lake response is basically two-dimensional. And this is often valued for small lakes where we can assume that the Coriolis force is negligible, but it's also often assumed to be the lake response in lakes where we have seen Kelvin waves, which are rotational motions, like Lake Tahoe and Mono Lake in Northern California. And on the other hand, we have the rotational conceptual model, or what we know as Ekman upwelling, where there is a lot of Coriolis force influence, and therefore our net water movement is deflected from the wind direction. And we know this as Ekman transport, and we expect the motions to be at about 90 degrees from the wind direction. And because of this, a strong Coriolis force, we have that when the wind blows along the shore, we see that the water is being pushed away from the shore at about to the right of the wind direction in the northern hemisphere. And as an attempt to balance this lack of water near the shore, we see the uprise of the hypolimmitic water to the left boundary from the wind direction. And these motions are basically three-dimensional. But what happens in the lakes that are in between? What happens in the lakes that are neither small or too big to be classified within these frameworks? I'm talking about rotational influenced lakes, different from like the Lautarian Great Lakes or like Lake Geneva, and something similar more to like Lake Tahoe. What happens? What are the dynamics that we experience during upwelling events? And knowing these dynamics is really essential for the proper prediction and planning of studies that pretend to assess water quality in these lakes. And so to address this question, I basically implemented a total of 400 numerical simulations using the numerical model SI3D, which stands for semi-implicit three-dimensional lake model, where I did a combination of the parameters that we're looking on the table. And I varied the length, the depth, the epilimnion temperature of the lake, the epilimnion depth, the metalimnion depth, and the latitude to consider different Coriolis force. And I implemented these length scales and Coriolis force in two different basins. This time I'm using canonical basins, a rectangular basin, as we can see in panel A, and then a circular basin, as we can see in panel B. All of the numerical simulations were forced by a wind pulse that were coming from the south to the north, and they were initialized by a stratification that considered a constant epilimnion, then a linear transition in the metalimnion, and then a constant temperature for the hypolimnion. So in all of the numerical simulations, all the dynamics were similar regardless of the length scale, which is the normal parameter that we use to know if our lake response during an upwelling will follow the two-dimensional model or the three-dimensional model. But in this case in particular, I'll be showing the results for a medium-sized lake, a lake with a length scale of 35 kilometers, which for the rectangular basins, I'll be presenting three different scenarios. The first one, A, the top panel, being really strongly influenced by the Coriolis force. The middle one, B, is a lake that is rotationally influenced, but not as strong as case A. And then we have the results for a non-rotational scenario of the lake with the same length scale. All these scenarios were parameterized by the Borger number, which is basically the ratio between the inertial forces and the Coriolis force. As you can see on the surface temperature, which I'm representing in here, the upwelling in the strongest influence by the Earth's rotation, we see that resembles what we would expect from the Ekman upwelling. We see that upwelling of the rise of hypolymitic water is to the left of the wind direction, and we identify this by the color blue, by the blue color on the surface water that has hypolymitic temperature of 5 Celsius. But we also identify this by the cross sections, where one states for south-north and the lake, and then 2 stands for west-east. And in this case, because it's Ekman upwelling, we expect that the tilt of the thermocline is dominant on the section number 2 from the west to east, as we can see in the results. Then if we look at the results for the non-rotational model, we see that it does behave like the 2D, regardless that this lake has 35 kilometers as a length scale. And we see that, again, upwelling is predicted correctly by being at the upwind boundary. And the cross-section that shows the dominant tilt of the thermocline is 1, which is in the same direction as the wind from south to north. But then there we have the middle case, where we see that there is a combination of both dynamics from these conceptual models that we know so far. We see that upwelling is happening at the left to the wind direction, but also at the upwind boundary, helping us to know that we'll expect water quality impacts from upwelling at both boundaries rather than just one. Similar results were found in the circular basin, where we still see this behavior of a dominant tilt of the thermocline from west to east, and in the west to east cross section, when it's Ekman upwelling, we also see that the tilt of the thermocline is dominant in the case of a non-rotational. But then in the combination, in this middle case, where we see the combination of the dynamics, we see that the thermocline tilt is equal or quasi-equal in both cross sections. So to basically summarize my study and just to give some conclusion and significance of my results, I group all the simulations into these two plots where we're looking at the rectangular basin and the circular basin, and I classified them by looking the Borger number on the left axis, and on the x-axis we're looking the length scale of each of the lakes that I consider. And they're colored by considering if they represent the Ekman upwelling, a rotational upwelling, which implies for the combination of the two dynamics, and then if they represented non-rotational upwellings. If we look at both the rectangular basin and circular basin, we see that Ekman upwelling is always expected to happen when the Borger number is lower than 0.2, implying that the Coriolis force is at least 5 times greater than the inertial forces. And that's why we see upwelling to be at the left boundary. But then the closed basin, or the 2D conceptual model, accurately describes the lake response for lakes that have a Borger number of above 0.8, implying that the Coriolis force is almost equal to the inertial forces, or when the Coriolis force is lower than the inertial forces. And then between these two thresholds, which were unknown until now, we have these lakes that show a combination of both conceptual models, where we have internal waves going not only perpendicular to the wind direction, but also parallel to the wind direction as well. And same with the barotropic gradients that develop during the wind forcing. So some of the significance of this study is that now on, I'm trying to, with like this parameterization and with these thresholds, we can sort of predict where upwelling is going to occur, and therefore we can better plan ahead our water quality studies when we want to address the impacts from chlorophyll or nutrient fluxes during upwellings in the nearshore areas that are of interest for our lakes. So yeah, and for future analysis, I'm planning on doing investigating the rotational influence post upwelling. However, so far we know that there will be rotational waves as a response to winds in any lakes that have a Borger number lower than 1. So if our Borger number is greater than 1, we expect that instead of creating Kelvin or Poincare waves, our lake will result in standing waves, or which is known by SAGE. And finally, to conclude my research, I'm planning on collecting data from lakes that I know they're rotational influence, but they are commonly assumed to have a non-rotational upwelling, to see where the upwelling occurs, where are the nearshore or like the coast that actually upwell during different wind events. So far, I have done it for Lake Tahoe, where I have seen that indeed the response is a combination of both events, and we see that upwelling occurs for a different coast and not just the upwind coast when the wind blows in the natural basin. With that, I think I consumed the time. So thank you for your attention, and I will appreciate again CALMS for the opportunity. And that's
great. Thank you, Sergio. I learned a new dimensionless number, the Borger number. I like it.
Right.
Questions? This is kind of a neat linkage here between kind of large scale hydrodynamics and upwelling, which of course can bring up nutrients and stimulate surface production.
Yeah, Mark, I have a question.
Yeah, go ahead.
And it's exactly what you just touched on is, we think of upwelling on the coast, of bringing all these rich nutrients and all this great productivity. But I'm not going to say I followed what Sergio said half the time, because it's way out of my area of expertise. But how does this relate to lake turnover and this upwelling that's bringing nutrients to the surface is not for lakes. It's not always a good thing, because we can see algal blooms and whatnot. So I'm having a problem identifying the difference between lake turnover and these upwelling events.
Turnover is when, at least my understanding, turnover is when from the bottom to the top, the lake mixes. But upwellings can occur at different depths. It's not necessary when an upwelling occurs, all the lake is going to go and mix. The water column is not going to mix completely. So upwellings can bring up nutrients at different coasts and different shorelines that might be of our interest. And I guess in terms of lake management, my biggest input will be that sometimes we consider a lake response to be in a certain way. And with this, we can see that natural systems that are not that big, like Lake Tahoe, we see that upwelling can occur at different coasts. And that's where we should pay attention when we try to assess these water quality challenges.
Great, thanks. We need to move on to our next speaker, but yeah, I mean, we have this idea of the thermocline during the summer and no transport, but that thermocline's moving around. There's lots of leakage around the edges and a lot of potential internal nutrient loading during summertime. Great, Sergio, good luck with your work. Thank you all students, great work. And it's just an honor to see what these young students are doing. They're the future in many ways. So, and thanks again to CALMS for the student support and for the professional support as well from the supporting companies. And with that, I'll hand it off back to Dina. Thank you all.
Yeah, thank you so much, Mark. Mark is the chair of our Student Scholarship Committee, and he always does a great job getting the announcements out and finding us some students that are doing some really interesting work. All right, next we'll move on to our keynote speaker for the conference. Our keynote speaker is Craig Williamson. He's the Ohio Eminent Scholar of Ecosystem Ecology at Miami University in Ohio. He leads the Global Change Limnology Laboratory, and he is passionate about lakes and protecting their water quality. His expertise is with the effects of UV radiation and other types of climate change on lake ecosystems, with a focus on the effects of changing water clarity. His research extends from the Pocono Lakes of Pennsylvania to the Laurentian Great Lakes to Lake Tahoe, and to subalpine and alpine lakes in the US and Canada, Rocky Mountains, Argentina, and New Zealand. His research questions range from the effects of UV on the ecology of zooplankton, larval fish, harmful algal blooms, and infectious diseases, to deploying advanced sensors to decipher the sentinel responses of lakes to climate change. He is the chief scientific advisor of the Pocono Lake Ecological Observation Network, an outreach program on public education and monitoring of Pocono lakes. He is active in the Global Lake Ecological Observatory Network, where he leads the Climate Sentinels Working Group. He also serves on the United Nations Environment Program Environmental Effects Assessment Panel, which reports to the United Nations annually on ozone depletion and UV effects on both aquatic and terrestrial ecosystems, as well as on humans, materials, and the atmosphere. And Craig, thank you so much for agreeing to speak. If you want to go ahead and see you're sharing your screen, I will let you take it away. Oh, Craig, I think you are still muted. Okay.
Okay, so you can hear me now.
Yep.
And do share here. So is that presentation mode?
So we can still see kind of just the normal PowerPoint view.
Okay.
That.
That better?
So we can still see, do you have two screens?
Yes, I do. So I need to switch
Yeah,
the screen
switch the screen that you're sharing, and I think we'll be in good shape.
Let's see.
Recording in progress.
How's that? Is that better?
Looks good. Thank you.
Okay, sure. So thank you to Dina and Alex for the invitation and organizing this. And thank you for the students who've just given some very interesting talks. I really appreciate the opportunity to talk across the continent here. I'm actually right now in New Hampshire, where occasionally we get the effects of the wildfires, and I'm still studying lakes out here. We get the effects of wildfires in California, actually, or Canada as well. So I want to start by letting you kind of absorb this picture, because this has a lot to say about what I'll be talking about. It's a picture taken by a professor at Sierra Nevada College, Steve Ellsworth, who caught the King Fire over Lake Tahoe back in 2014. And you can see a huge amount of carbon, biomass, effects on light, and effects on lakes. And we heard a nice talk already this afternoon on effects on particulates by Kenneth. Thank you very much for that. I would like to thank our group too. We have a very active global change limnology lab, We specialize in ultraviolet radiation, as Dina had mentioned. And the work I'm going to be talking about here is work that many students through the years and colleagues have been involved in. And at the heart of this has really been Aaron Overholt, my lab manager. Work is supported by Miami University, as well as the National Science Foundation and a whole variety of other funding sources. So let's start out 350 to 450 BC with the basic roots or elements of life according to ancient Greek cosmology. This is Aristotle's diagram of some of the elements here. And we're looking here at fire versus water. And let me see if I can get my spotlight here. It's not working. There we are. So fire and water, earth and air, you've all heard about this. Again, the four elements of life. Fire and water are opposites. Fire tends to rise, water tends to sink, and these interact with each other. This is interesting. These tend to interact with each other through earth and air. And you can think about this as the terrestrial watershed being earth and the airshed being the air component of this Greek cosmology. And what we're seeing now is a shift to a hotter and drier climate that favors fire conditions. So again, we have fire and water interacting through earth and air and mediated by meteorological conditions that range from hot and dry to wet and cold. Again, all opposites in this fundamental elements diagram. What this has done is lead to a greater likelihood of wildfires, as we all know. So with that little bit of Greek background, let's take a look at some of California's lakes. Some of the most beautiful lakes in the world, for sure, and I've been very fortunate to study a number of them, ranging from some of the Sierra Nevada high elevation small lakes like this one, a visit hosted by John Milak, UCSB, and some of my students here. Lake Mono, of course, very different from these high elevation small alpine lakes. And then Lake Tahoe, huge range of really beautiful lakes. One of my favorite things about these lakes is that you bring your students there and you get these ear-to-ear grins on their faces because it's such a beautiful place to be sampling. And the water resources are so precious. So these lakes are unusually clear. And as I mentioned, I tend to work on ultraviolet radiation. And so this chart shows the depth to which ultraviolet radiation of two types, UVB, very damaging, somewhat less damaging UVA, penetrates in lakes all over the country. And what you'll notice is that these are the quartiles. So in about 75% of the lakes, you can see that UVB doesn't generally go down deeper than a meter or so. In some cases, it goes down to 2 meters in the Southern Blue Ridge, but it's really not until you get out to the west that you get the real high water clarity where the UV will penetrate down to 4 meters or more. In fact, the UVA will penetrate down to 10 to 12 meters or more. So even though I was taught initially that UV doesn't penetrate any further than perhaps a few centimeters, we found, no, this is not true at all. In fact, in Lake Tahoe, one of the clearest lakes in the world, UV can go down to depths of up to 25 meters or more for the UVB, the damaging UV. This is how deep you are in the water column here, a typical limnological graph, starting from 100% and going down to whatever depth it is for the 1%. This is 1% of surface irradiance. And same thing for the UVA, except that goes down to close to 50 meters. So the point is that UV penetrates deep in the clear western lakes and can be a significant factor here. What about the weather conditions? What about the fires? What about the droughts? We know that these lakes are embedded in a location where there's not only severe drought, but extreme or exceptional drought. And this extends over a good part of the country. This is the Drought Monitor Map from just this last week. Don't need to tell you about this. There also is a real pronounced relationship between drought and wildfires. The 20 largest wildfires are, for the most part, occurring larger and during periods of more severe drought. The negative PDSI here representing the more severe drought. And here are the rim fires and king fire that we studied quite a bit a few years back. More recently, we take a look at 2021 CAL FIRE incidents as of October 4th. We're talking about over 7,000 incidents and on the order of 2 million acres. This is more than twice the area of the whole state of Rhode Island being burned. So this is a substantial amount of burning. But most of this is not new to you all, other than perhaps the UV components. And that's what I'd like to focus on here. I want to look at the effects of ultraviolet radiation on lakes. I then want to look a little bit at the fire effects, or the effects of fire on exposure to UV radiation in lakes. And then I want to get back to the ancient Greeks. Did they have it right or not? We'll take a look at these three major topics here. So let's start with the effects of ultraviolet radiation on lakes, but let's start with even something more familiar, and that is the effect of sunlight with full UV radiation on humans. Imagine going outside during the summer in the middle of the day with no clothes on and lying down in the sunlight. There would be very severe consequences. Very severe burns, blistering, eye damage. In fact, you can go blind in a couple of minutes by looking at the sun. Longer term exposure at lower levels, you get mutation, skin cancer, cataracts, pterygium. The point is that UV radiation out there is deadly. And of course, we as humans can largely avoid this behaviorally because we know this, even though we can't actually detect the UV. But what about lakes? What effect does sunlight, full sunlight with UV radiation in it, have on lake ecosystems? If we look at some of the key players here, for instance, Daphnia is a keystone zooplankton grazer. They die after less than a day of exposure in the surface waters. Of course, they tend to migrate down during the day, and this is why they'll survive. They can detect UV and migrate down to avoid the UV radiation. We've shown that in a number of studies. Larval fish, highly transparent. Many of them are positively phototactic, attracted to the surface waters, and they can perish within one day of exposure for some of the more sensitive species. So UV radiation has a really pronounced effect here. If you incubate fish eggs, in this case, yellow perch embryos, in the surface waters at a depth of about 0.8 meters in a clear lake, if they're exposed to UV, they all die. If you shield them from UV radiation, they survive and hatch. You can see the well-developed embryos here on the left-hand side of the slide. So that's what happens with too much UV. What about too little UV? There's some benefits to UV radiation. For example, vitamin D. It's the same very short wavelengths of UV radiation that are highly damaging that cause the production of vitamin D. And without enough vitamin D or a vitamin D deficiency, you get rickets. So we have a situation here, these are bone malformations, of course. We have a situation where too little UV radiation leads to negative effects in humans, too much sunburn. So there's a level of UV exposure, which is just right, which is more healthy, somewhere right in the middle, where you get adequate vitamin D production and you don't get burned. What about in lake ecosystems? Lake ecosystems are obviously much more complex than just the human body. What happens if it doesn't get enough UV? Can this be a negative effect? And in fact, the answer, as you might expect, is yes. Solar ultraviolet radiation is the most effective natural disinfecting agent, something very relevant to the pandemic these days. SODIS, or solar disinfection of drinking water, has been used for decades to disinfect drinking water. You put water in a bottle, you expose it to the UV and sunlight for a single day, and you've disinfected it of pathogens. It becomes much, much safer to drink. Of course, the timing is really important on this. And this potential for solar inactivation, or what we might call the solar inactivation potential, varies a lot seasonally. So here in Lake Tahoe, very, very clear system, there's a very, very high solar inactivation potential during June and July. And it, of course, declines during the fall and winter or during the spring. So there's a strong seasonality here that depends on the angle of the sunlight, the season. And this would be the middle of the day, actual day's exposure in the top meter or so. Other lakes, which have higher concentrations of dissolved organic matter, do not have as high a solar inactivation potential. And so they have potentially more pathogens, more human pathogens and more pathogens for wildlife as well. So there's variability, seasonality, seasonally, and variability among lakes. There also is a seasonal variability related to drought. So what you see here is a graph that shows the transparency. This is the depth to which the UV penetrates during, quote, normal years. For instance, 2007 to 2013 in the blue here. UV might penetrate down to something on the order of 20 or 25 meters. However, during drought conditions, like 2014 and 2015, strong drought years, the UV can go down to depths of 30 to 35 meters, in particular during the summertime. So again, much higher UV transparency, which obviously is going to have a pronounced effect on the biota. It can have a pronounced effect on larval fish species, zooplankton, and a number of other things that I'll talk about in just a minute. First, let me mention dissolved organic matter. Think of putting a tea bag in a teacup, and that brown stuff that leaches out is dissolved organic matter. Think of a leaf on a sidewalk, that brown stuff that leaches out is dissolved organic matter. And if you think of this happening throughout the catchment or watershed of a lake, you get a substantial amount of dissolved organic matter that can enter the lake and turn the water to a brown color. And the important thing here is that this dissolved organic matter selectively absorbs ultraviolet radiation, and particularly the shorter, more damaging wavelengths. And so if you get a storm event, for example, something else that's a result of climate change, higher precipitation events like you see here in June, high precipitation, this is in Lake Michigan, followed by high discharge. And here's a visual of the discharge into Lake Michigan. And what you can see here is very high concentrations of dissolved organic matter. And of course, a consequent reduction in the depth to which the UV would penetrate in a system like this. So while droughts tend to increase water clarity, to UV in particular, if you get flood conditions, high precipitation, extreme events, the opposite happens. You get high concentrations of dissolved and particulate material that will absorb the UV and prevent things like, or minimize or reduce solar disinfection. These are some data from one of our lakes in the east, taken immediately before and then after a storm event. And you can see that this is visible light. And before the storm event, the visible light went down deeper than 15 meters. After the storm event, only down to about 10 meters. And the same thing happened with the ultraviolet radiation. You can see the UV in a lot of the eastern lakes doesn't go anywhere near as deep as it does in some of the California lakes, as I had mentioned earlier. But the important thing here is as you get bigger precipitation events measured here in millimeters per day, because the events can last for different periods of time, ranging from a few hours up to many days. As you get increase in precipitation, you get a decrease in the transparency. So this is the transparency here. Dashed line is no change in transparency. Drought conditions, as I mentioned before, increases transparency. This would favor the wildfires. And flood conditions decreases the transparency up to 7% per day when you have high levels of precipitation. So the weather conditions are very important to the transparency in the lake here, and the drought conditions or the flood conditions, which are certainly connected to the wildfires. Thinking some more about the effects of UV, let's take a look at effects on invasive species. And here we have 3 species that occur in Lake Tahoe, the bluegill and the largemouth bass, which are warm water invasive species. And we also have the Lahontan redside, which is a native species. Notice the higher levels of pigmentation in the redside versus the highly transparent bluegill and largemouth bass. And if we expose these to UV radiation, this is mortality rate on this axis, and this is level of UV exposure in the sunlight in the vicinity of Lake Tahoe. And what you can see is the invasive species die off at a very low UV level, the bluegill and the largemouth bass. The native species can withstand much higher levels of UV exposure and survive quite well. So they tend to be very UV tolerant. And so the point here is that the high levels of UV can help exclude invasive species if you can keep Tahoe not only blue, but if you can keep Tahoe high transparency. And yet the native species survive just fine. So this is one of the another potentially positive effect of keeping Tahoe blue, keeping the transparency very high in all of the California lakes. There's another role for UV radiation, and that's with mosquitoes. There's concern about invasive mosquitoes coming from subtropical areas, some of which carry serious diseases, human diseases and others. And these ranges of these species, these Aedes species in particular, are extending well up into the United States, including up into California. Previously subtropical species are now extending into more temperate areas. And so what about their sensitivity to UV radiation? The larvae, for instance, grow up in aquatic environments. And we have found that if you expose them to UV radiation, the larval survival, this is the survival of larval mosquitoes exposed to UV radiation in the sunlight out in a solar exposure apparatus like this, held in a water bath, much lower survival than if you shield them from UV. And if you bring them inside in a constant UV exposure apparatus, if you shield them from UV, their survival rate is very, very high. If you expose them to UV and there's no dissolved organic matter, they all die. If there's dissolved organic matter present, many, many more survive. So the message here is that, again, UV has a potentially positive effect in terms of minimizing adult emergence of these disease vectors in mosquitoes. The larvae, as you may know, have breathing tubes and have to stay right up at the surface. So if you have low dissolved organic matter and high UV exposure, this kills them and they never are able to emerge to adults. In contrast, if you have high dissolved organic matter and low UV exposure levels, you basically have a refuge from UV in high dissolved organic matter. These larvae can pupate, survive, and emerge as adults. So again, UV can be an important mechanism to control these vectors of disease. And you have situations like this. These are from some pictures from Lake Tahoe. On the left, undisturbed Sand Harbor, and on the right, more highly disturbed, higher DOC Star Harbor. And you get very, very different systems here in terms of the UV exposure. And the high DOM in particular, again, will lead to low UV exposure and create a refuge for invasive warm water fish and mosquitoes. Okay, so that's a quick primer on ultraviolet radiation effects on lakes. And the point is that in spite of the fact that UV is mutagenic, carcinogenic, can be lethal within a short period of time to many aquatic organisms that occur near the surface, it also can have some really beneficial effects in terms of disinfection, reducing vectors of disease, and excluding invasive species, native invasive species. So now let's bring fire into the question here. How does fire affect UV exposure or exposure to UV in lakes? We'll look at both the watershed and we'll look at the airshed. We already looked a little bit at the watershed in terms of the DOM, dissolved organic matter, coming into the lake and turning it brown and reducing UV exposure. Smoke does a very similar kind of a thing. This is the King Fire right next to Lake Tahoe. This is actually the fire on the same day of the initial picture that I showed that Steve Ellsworth took of the smoke clouds over Lake Tahoe. In some cases, these fires, in this case, the Rim Fire, 2013, third largest in California history. Remember that for later on, going right over Lake Tahoe and having a big effect on the incident solar radiation there. And the important thing here is that smoke, like dissolved organic matter and like ozone, selectively absorbs that short wavelength UV that is so key either to mutations and lethal conditions in the surface waters, but the smoke also selectively absorbs these short wavelengths to the detriment of the lake ecosystems, in that it can increase parasites and provide a refuge for mosquito larvae and for invasive species. So ozone is the most highly UVB absorbing, then dissolved organic matter, and then smoke. So smoke is not quite as strong as the other two, but it's still an important factor. And in many cases, we have smoke that extends over quite a wide geographic range, as I think you know well. These are some data collected from the Environmental Education Center, TERC, on Tahoe. And this shows the changes in UV radiation relative to PAR or visible light, think of it as visible light, at Lake Tahoe following the Rim Fire. So the gray here is the 2009 to 2012 average, what you would normally see when there are not big fires. During the Rim Fire is the red. Onset of the Rim Fire, smoke plumes over the lake, as I was just showing you. Big reduction in the UV relative to the visible light in particular, and then the Rim Fire burns out and there's a recovery there. So again, what we're seeing here is the smoke plume substantially reducing the exposure to UV radiation, and particularly those really dangerous short wavelengths that also serve to disinfect and protect or create a refuge, I should say, from damaging UV, for instance, for mosquito larvae and invasive species. And this isn't just back with these fires that we studied to a great extent. It's happening right now. This is October 4th photo taken right out of the Sacramento Bee. Some of you may have seen the KNP complex and the air quality over the Fresno area. This is bad enough to issue some air quality alerts for this region. And I'm sure you're all familiar with this. And it's not only limited to a small local area either. when you get these fires, this is a good example here. You get an incredible smoke plume that can cross all the way across the United States and even further. This is the rim fire, I believe it was. So it's affecting air quality even on the East Coast. And there's some beneficial effects here if you enjoy sunsets. This is the sunset brought to you by the fires in the West. A picture that I took over a lake. You can see the sunset reflecting in the lake here. A vivid red color due to these incredible smoke plumes. Again, demonstrating the effects even at long distances. You often see this intense haze. We saw it this summer as well from the intense fires out in the West and the Canadian wildfires as well. And it's not just in the United States. So here we have the rim fire, which is certainly making a plume, in this case, carbon monoxide, over a good part of the United States. But look at how it's really just a relatively small flash in the pan compared to the biomass burning that's going on in regions of Africa and Asia, and the huge smoke plumes that are altering the UV exposure environments over vast areas of the oceans as well as inland lakes. So while this is a California Lake Management Society meeting, I think it's important to put this in the larger context. That's my perspective as a global change limnologist. These issues are not just limited to California, but they're going on really around the world. Okay, so did the ancient Greeks have it right in terms of interactions between fire and water through the effects on earth and air? And here we see there, this is Aristotle's diagram, fire, water, air, and earth. We have the conditions being promoted by climate change with the warmer conditions, the hot, dry conditions. We have the fires as the result, devastating the watersheds, the terrestrial watersheds, the earth around the system. We have the smoke plumes polluting the air very severely and reducing the incident UV. So you get a lot of incoming solar UV as well as visible light goes through the smoke plumes, and the exposure to the lakes is much, much lower. So there is a substantial effect there. In addition, as I mentioned earlier, we get heavy precipitation events at times. Of course, there's a higher evaporation due to the hot, dry air, and you get more precipitation. This more precipitation, when it falls on the surrounding watershed, leads to input of this dissolved organic matter, turning lakes a browner color and reducing UV exposure there as well. So overall, these fires have profound effects on lake ecosystems through these two major mechanisms, through ravaging the terrestrial landscape and altering the inputs of dissolved organic matter into the lakes, and by creating large smoke plumes, which reduce the UV exposure, with consequences, again, for a wide variety of health issues for humans and the lakes themselves, the lake ecosystems. And you're probably all aware the projection for the future is not very bright. There's a projected increase in very large fires, as shown here from the US Global Change Research Program special report. And this is not limited just to California, but it goes all the way to the northern Midwestern United States and even the Southeast. In the Midwest, up in the area around Minnesota, you probably are aware of some of the boundary water fires that occurred this past summer, July 2021. This is the Boundary Waters canoe area here. And this is a close-up showing the Boundary Water canoe area that was closed due to wildfires up in that area. Each little red dot there represents a closed campsite. So again, a situation that's not limited to California, but limited to even areas that we don't think of as particularly hot and dry, but areas that are very, very rich in lakes like Minnesota, of course, the state with the land of 1,000 lakes. There are issues of human health, which have been mentioned before already by some of the student talks here. You've probably heard just in this last month or so, 200 leading medical journals declaring that climate change is currently the greatest threat to human health. And according to the World Health Organization, a combination of not only outdoor, but also indoor household air pollution is important as well, cause about 7 million premature deaths each year. So yes, COVID is a huge problem, but air pollution is, in terms of premature deaths, a huge, huge problem and something we can do something about if we have the will. And it turns out that the fires are really adding to this. The talk that I believe was Kenneth gave earlier talked about PM 2.5, and these are the most toxic. They're really tiny, small particulates that are very, very toxic. And it's frequent that the EPA limit for these particulates is higher than, I mean, the levels from the wildfires are higher than the limit, even 1,000 kilometers away. And the local mean levels can exceed by 10 times or more the EPA limit and reach really hazardous levels. So the effects of wildfires, again, are wide and varied. Their effects on UV radiation, an angle that most people don't think about much, in spite of the fact that the UV has very strong negative effects on humans. Again, sunburn, mutation, cataracts, blindness within a few minutes, very powerful force we don't think about too much because we can't really detect it other than after the fact in a sunburn. Has a similar, very strong effect on lake ecosystems. And some of it can be, particularly in the very highly transparent lakes of California, the UV can have some very positive effects in terms of reducing or protecting lakes from invasive species, from vectors of disease like mosquitoes, and by disinfection, by solar disinfection of pathogens. But there also are other components, again, that are a little more obvious. We think a little bit more about in terms of the smoke effects, in particular, like breathing the particulates themselves. And that's it. If anybody has any questions, I'd be happy to answer some questions.
Greg, thank you so much for your talk. It looks like we have a couple of questions in chat, so I'll start with those. From Stephen McCord, he wants to know, do fish respond to their UV exposure? So if sensitive invasive species are in Tahoe, they'd stay at deeper depths?
So that's a really good question. And we don't really know a lot about the behavioral responses of fish. There are several studies that have showed that some salmonids, for instance, avoid UV radiation. But there have not been a lot of studies on that. And I can't tell you whether the species in Tahoe actually show that avoidance response or not. But it definitely could alter the distribution, the vertical distribution. And a recent paper by Facundo Scordo out of Sudeep Chandra's lab has shown changes in fish populations avoiding the shallow areas in particular in years with wildfires. Some data, some nice data, a nice paper out of Castle Lake, Northern California. We do know that the zooplankton, we've documented the zooplankton migrate deeper in the lake when they're exposed, and when there is a smoke plume from wildfires coming up over the lake, they tend to occur at a shallow distribution, which of course could alter their availability to fish as a food resource.
Thank you. Okay, our next question is from Joe. He says, Sierra lakes are full of non-native trout. I'm curious how the UV control theory translates to them.
So again, a really good question, and I wish we had more information on UV and all kinds of fish, salmonids in particular. Some of the trout species, of course, the salmonids, tend to occur or have evolved in very high transparency systems and often very shallow systems. So some of them can be relatively tolerant. and are some of the more tolerant species that we've tested when we look at their eggs and larvae. But the older fish are going to tend to be more pigmented and more resistant. So the point is that there's some sensitivity for sure in the early stages, but where the eggs and larvae actually occur will make a big difference as to the level of UV exposure and whether or not they'll be influenced by exposure to UV.
Okay, we have another question in the chat from Stephen. Have you observed changes in water quality, read nutrients, from wildfires that impact primary productivity or due to the reduced UV exposure?
We've not directly tested for productivity in terms of the UV exposure, but certainly there's the potential for the release from photoinhibition as you get wildfire smoke in particular, and as you get some of the particulates that will tend to build up in the surface waters. And I've not looked in terms of the nutrient content myself in terms of the effects of nutrients from wildfires.
I think that would be really interesting, yeah, to
It
look
would
at
be,
how
absolutely.
those
And
nutrient
Sudip
changes.
Chandra is on top of that, has assembled a really nice group of people to look more at the productivity, nutrient, including the light and UV angles as well. And hopefully we'll have some better information on this. There are some past papers by Charles Goldman and others that did look at productivity in terms of the potential effects of nutrients. And there is certainly some signal there for it. It's not something I've dealt with a lot myself, though.
Okay. Our next question is from Mark Butel. Is there a connection between UV and harmful algal blooms? It seems like cyanobacteria can handle it all. Do you know if cyanobacteria, with all of their complex pigments, are more competitive under low UV or high UV?
Well, that's, again, a really good question and something we have relatively little about. In fact, I dare say that UV is probably the most important forcing factor in lakes relative to what's known about it. But a lot of the emphasis there is on the fact that we know very little about UV and many components of it, in spite of many years of research. And harmful algal blooms, cyanobacteria, many species are in fact very, very resistant to UV radiation, more resistant than some other species are. They do have some UV protective compounds. I think the most important thing here is dissolved organic matter and the fact that dissolved organic matter absorbs UV, but it also can carry nutrients with it, and the UV can potentially release those nutrients. So it's a situation where we think that dissolved organic matter has a strong effect on harmful algal blooms. We don't really know at this point whether there's a positive or negative effect, but one of my PhD students, Lauren Knows, currently has some support to work on this in the Great Lakes. And we're looking at the effects of all kinds of dissolved organic matter on it. We won't be looking directly at the UV component, but the nutrient component of that.
Very cool. Those are all the questions I see in the chat for now. If anyone else wants to ask a quick question, feel free to unmute yourself.
This is Alex, can you hear?
Yes.
I guess you didn't see my question, but I've watched,
I'm sorry, did I miss it?
Well, you read it.
I don't see it in the chat here. Do you mind reading it?
Okay. I said, I've seen thousands of acres of cyanobacteria on a lake surface die in an hour around noon. And that's too fast for cyanophages. And this was back in the 70s. I've always assumed that this was UVB. What does our guest think?
Well, certainly a fascinating observation. It could be that if they were brought up to the surface, not well acclimated to UV, very, very high exposure in the surface waters of a low DOM lake, that UVB could do some damage. I've never heard of an event like mortality rates that high, that quick. how did you actually detect that they died and they didn't somehow disperse?
At the time, I had a satellite, a U-2 flying plane or something, and my own plane, and I was on a boat right in the middle of it, and we watched it change. I was sitting there and it was all green, and we're taking samples of chlorophyll to do what I call water truth with the remote sensing. This is in 1972, the early days of remote sensing, and this has happened before. And suddenly it all goes, and you can tell, of course, because when blue-greens die, they put out trillions of gas vacuoles, so it all goes white.
Okay.
And
fascinating.
It's the lake's eutrophic. DOM is probably not very low, but of course these things are right on the surface. I mean, they're within what, 2 centimeters or a centimeter. They're 5 centimeters thick at thickest, so they're really up against it. And of course they're nitrogen limited in these kind of lakes, so they're not too healthy, which is why they're floating, because otherwise they'd make glycogen and sink. So they're obviously unhealthy because they wouldn't be there at noon. They're too clever for that. They would go down by making glycogen in the morning. They don't, and that's when there's a nutrient shortage or some other factor affecting them. But I've never seen it so dramatic as this one particular case, but it does happen quite often.
Yeah, that's really fascinating and certainly very suggestive. And UV can, again, have a negative effect, whether it can kill that many in that short period of time. We'd have to put out a UV protective film on the lake during one of these events and find out.
Well, I was just looking at your photographs of people, and that didn't take too long.
Yeah.
Anyway, great talk. Thank you.
Okay, thank you.
Okay, thank you, everybody. Thank you, Craig, for giving our keynote address, and congratulations to all of our student scholarship winners. Yeah, this was a great conference week, and we thank you all for joining us virtually, and hopefully we'll be able to meet in person next year. All right, thanks, everyone.
Thank you, Dan. Take care, everyone.
Good meeting, really good. Thanks.